We saw that when we have a structure of electrons spiraling, going around a nucleus, we can uh, identify their energy. They, the further they are from the nucleus, they have higher energy. So their Coulombic potential changes by 1 over r, and a time comes when there is no potential. So they have the highest energy at that time. Now, between the idea of an atom in free space, an atom that may be a number of atoms next to each other, the things that are part of an atom, nucleus would be at an exact distance from each other. We can exactly kind of locate them, but their electrons would be now shared. The electrons would be now shared between two adjacent atoms, not just on, if you think about XYZ axis, and if you remember unit cell, one atom would be connected to, at least for silicon, if you think about it, it would be a bunch of atoms that it would be connected. One could be XYZ, and then there was that face-centered cubic, face-centered atom, and then there was an atom which was A divided by 4, B divided by 4, and plus C divided 4 away, right? In a 3D space. So there are, but we know that it's a group 4 element. So it's sharing its electron with 4 other atoms. They are close by, but the sharing happens between 2 of them. Now, going from this free space to part of a system where a bunch of atoms are coming together, that's going to change our Coulombic forces. That's going to affect how electrons move around. And this is something which gives us an idea of what we call energy bands. We have touched upon band gap energy. We have talked about conduction band, valence band before. But today what we are going to do is we'll look at that when these atoms are brought together, what are the forces of attraction and repulsion, and how do they balance? And when they balance, how does the electric energy change? And now with the knowledge of Pauli exclusions principle, now with the knowledge of energy band and subbands, how does this all fall into place? And we will look at, and that would directly translate into electronic properties or electrical properties of solids. I say solids because a solid can be an insulator, metallic, or semiconducting, right? So all those, and a solid can be crystalline and a solid can be non-crystalline. But what's important is we have to understand how the what do electrical properties really depend on when we talk about atomic level or subatomic particles. We saw this picture before, and nothing but just a 2D way of looking at nucleus, distance from the nucleus, and energy levels. And we said, okay, there's lower energy levels, we call them valence level. There is ionized or zero energy level, which is further away from the uh, nucleus. Now, there is that idea that every electron has its own set of quantum numbers, NLMS, which means the N, if you remember, N was for energy. So it has a very specific energy associated with its shell. And when an electron would leave its parent atom, it has to have a higher energy than an electron which is close to the nucleus. So essentially, when we talk about sharing electrons, we talk about electrons which are further away from the nucleus. Now, I'll come back to this slide, but let me just show in a picture where I'm showing you kind of two of those uh, valleys. You see there is this dotted line. So I'm just going to build it. So you see, so there are two of those electrons, nucleus valleys, that we have brought together. We have brought them together, and we say there are some electrons which whose wave functions are symmetrical to each other. There are some wave functions who are anti-symmetrical. Okay, what does symmetrical mean? From NLM as quantum numbers, anybody remembers what was S? We had N, L, M, and S. S was for spin. So when you talk about subatomic particles, there are some particles which have a whole number spin. There are some particles like electron which has half number spin. So what we use to define spin, we use S by 2 to explain if it's an upward spin or a downward spin. So we use plus S by 2 or minus S by 2. And that helps us satisfy the requirement of Pauli's exclusion principle, that no two electron can have same set of quantum numbers, which means even in one same orbital, if there are two electrons, they may have N, L, and M same, but their S would be different. One would be clockwise, or other one would be anti-clockwise. So we would call one as plus S by 2 and the other one as minus S by 2. Now, I just want to take this idea from this slide away, and then we'll come back to it, and then we'll look at other things. Right now, just this idea that if you bring two atoms with their own Coulombic potential and its electrons together, their potential diagram is they're going to affect each other. When they affect each other, they're gonna either support each other, bonding, or they're gonna be opposite to each other, what we call as anti-bonding state. Now, there's another thing that when we bring them together, the two electron wave functions, they would be linear combination of individual atomic orbitals. This is a term called LCAO. I just said it and I'll write it. So they are nothing but linear combination LC of individual atomic orbitals. So what does that mean? So it means orbital 1, an orbital 1 from one atom, an orbital 1 from another atom. They would create a net orbital, which would be a linear combination of those two. Just simple. If you talk about second orbital from one atom and second orbital from atom 2, when they come together, they'll just form a linear combination of those two. Now, in those, there will be two kind of combinations. We call them odd or anti-symmetric, and we call them even or symmetric combination. Now, what's the difference between two? Now, there are electrons which are at different energy levels. The ones which are higher value of the wave function, they would be what we call as bonding orbital. There's this graph on the next slide. Let's go to that. So that's what makes sense now. That once we bring them together, there are two wave functions, psi1 and psi2. Nothing but they are explaining or depicting two atomic orbitals, two wave functions of two atoms. If they are, now they are a linear combination. So if they are anti-symmetrical, we call them so there are, if they are anti-symmetrical, they are anti-bonding. They are making a wave function which is going in the opposite direction. It's not adding up. And the other one is what you call as symmetrical or bonding orbital. Now, bonding orbital has higher energy, higher value of the wave function because they are adding each other. Now, wave function is basically the probability density function, which tells us what is the probability of having an electron there. Now, the bonding orbital shows us that there is higher probability of finding an electron than the anti-bonding state. This is what is the basic concept of the covalent bond. A covalent bond is where there is higher probability of finding electrons. Now, once this is formed, these two atoms are sharing those electrons. We cannot identify which electron belongs to which atom because they are now shared, they're part of both. Now, when we get this situation, the lower energy bonding orbital and higher energy anti-bonding orbital, as the systems in the universe, the things are stable which have lower energy. So there will be electrons which will be higher probability to be found in the lower energy bonding orbital, which is the lower one. Now, there is another thing that every wave function of electron has two parts to it. One is spatial, that where is it orbiting, and one is its spin around its own axis. So it's shown that when the spatial part is the symmetrical, that they are sharing the same space, their spin would be always opposite to each other. And that satisfies the Pauli's exclusion principle. Now, when you bring two electrons together, they would have opposite spin. But if they have same spin, they would repel each other, which means they would not want to be together in the same place. Now, this is not the same thing like Coulombic repulsion, but it is a quantum mechanical repulsion. Now, when we have two nuclei which have their own Coulombic potential, when they come together, the potential goes down. Instead of if they were separately away from each other, but now their Coulombic potential goes down. This is what is shown here at the lower level. So instead of this thing going up and up, this is now much lower Coulombic potential between those two. Now, when the Coulombic potential is low, it's lower energy. So potential energy is lower in this region. Now, in this place, the electron has less energy because now it's being attracted by two nuclei instead of just one. This is important to know that when an electron is shared by two atoms, it has lower energy. The simple reason for that is that when the two Coulombic potentials come together, their net result goes low. When the Coulombic potential is low, the electronic energy is low. And this is lower than if the electron would belong to a free atom in space. Now, if it is low energy, it is happy there. It would be moving around only in that lower energy potential. Now, if there are a bunch of electrons, hundreds of electrons, they would have bunch of very, very closely spaced energy levels. So what we call suborbital or sub-energy levels. What we call them band of energy levels. So in this place, then we have band of, let me move around the pictures. Number of energy levels where electrons would go and they would fill them up. So essentially it is not going back to the quantization. There's no continuous spectrum, but instead of that, there are a bunch of those, and we band them together, and we call this whole thing as a band, energy band. And this highest level that it can contain, we call it valence band. So all the electrons below that are occupying bunch of energy levels, lower levels of energy, right? So I'm just depicting electron in various energies. Now, these are just two atoms shown. Now you think about bringing together hundreds of thousands and millions of atoms. When they all will share these things, let me see how can I leave this on the screen instead of deleting that. All right, let's see, save. Okay, let me leave this here so to see if I can change the slide without changing it. Okay. Now we have hundreds and thousands of atoms, we bring them together. They all will contribute these energy levels with each other. And when you have hundreds and thousands of atoms, they have uh, even 4 times. For example, for silicon in the outermost shell, there are 4 electrons. So if you have 100 atoms, you have 400 electrons for them, right? Make sense? Now, for each of that electron, we cannot identify which atom does it belong to. But what we can surely identify is what is its energy level, right? So for us, it becomes more important to talk about energy band instead of individual electrons' energy, right? So that's why we get into what we call as band gaps. Now, you say that we have identified a level where these electrons can stay at lower energy level. But we also show there are two kinds of energy levels created. One is called anti-bonding, one is called bonding. So lower level is bonding, upper level is anti-bonding. It's there, it's available. Now, when we would give high energy to an electron, it would jump and go to anti-bonding level. And that's where it will become available to move around. That's another concept. Here at the lower level, we have bunch of electrons. They are packed together. They are packed together. There's no place for electrons to move around freely. But if an electron jumps and goes to higher energy level, there are not many electrons there. If there are not many electrons there, which means it can move around freely. That's what we call as conduction band, right? Just hold on with me on this concept. We'll come back to this soon. All right. Now, when we bring these two atoms together, the spacing goes smaller and smaller, and the electron wave functions start to overlap, right? When that happens, there are no two electrons which are in the same quantum state. Remember Pauli exclusion principle. So there is at most one electron per level after we split the discrete energy levels of the isolated ones together into one. So these levels, this is lower level is valence band, the upper level is conduction band, and the middle one is what we call as forbidden band, because there is no energy state for electron to fill. There is this region where electrons cannot stay. They have to either stay in the bonding or they have to jump into antibonding. So this middle region is called forbidden zone, or we call it band gap. Now this should tie back to, we talked about band gap before, but today we learn, okay, where does band gap come from? Now, if you were to find out exactly how many sites are there, we take an example of hydrogen atom. Oh, sorry, silicon atom. Let me clean the screen. All right, let's go back. Let's make sure we covered whatever I talked about. So we saw this. So Coulombic potential wells of two atoms close to each other along the wave function of two electrons centered at the two nuclei. So they are, when they come together, the net composite is linear combination of the two atomic or more individual atomic orbitals. So there are two of those, antisymmetric antibonding or symmetric and bonding material. One is high energy, unsustainable. One is low energy, where all the electrons are filled. Okay, now when we have, this is the same thing what we just talked about. When we have two of those come together, it's the same thing that we discussed. Now this is the important figure. So instead of looking at the figure, let me present an idea here. So when you have one atom with say X number of electrons coming together with another atom with another X number of electrons, when they come together, the total electrons are 2x, 2 times x, right? They are double. Now, if you talk about first orbit of one atom, first orbit of the other atom, when they come together, you have 2 times the first orbit. Similarly, you have 2 times the second orbital, 2 times the third orbital. This is what is shown here for a silicon atom. Now, what's the idea here? The idea, if you start from left, we start from left, we have two energy levels, and we bring them together, we bring them closer and closer to each other. A time comes, which is shown here, a distance comes, which is shown here. At that place, there are 4 times n states and 4 times n atoms. So there is, we suppose that there are 2n electrons in 3s orbital, and there are 2n electrons of one and the 2n electrons of the orbital of the other atom. Now, when we bring them together, so they are full in both sides. When we bring them together, all the states are full with all of those electrons. This is what it says. Now, at that time, you have this area called band gap, but on the other side, the, the higher energy area is empty, completely empty. There is no electron there. You can keep on bringing those atoms together closer and closer physically. And what it would do is this intermediate distance will keep on becoming smaller and smaller. Time will come, there will be no intermediate distance between those two. And you can keep on pushing them. And physically then, there will be some electrons which will be now in the higher energy level, the anti-symmetrical region, than here. But if you go back to that idea of what we used to call lattice constant, this distance is unstable because it is smaller than lattice constant. But this distance is exactly what is called the lattice constant here. Remember that lattice constant, what we wrote as A, small a? Now, at that stable condition, we have all the states full. In the conduction band, there is a band gap, and all these states are empty in valence band. Sorry, I said it the other way around. All the states are full in valence band, EV. All these states are forbidden in band gap, and all these states are available in conduction band. Now, what does it mean for us? It means for us that when we are talking about the crystalline structure of silicon, we bring together atoms and they all are completely isolated. But when we bring them together, we create states where some states are low energy, some states are high energy. All the electrons are happy in lower energy. And then there is a region where they cannot exist because there are no states, but we can apply, there are four things. What was that? Light, we could apply heat, we could apply voltage, or we could shake them, the mechanical vibration, to make electrons jump to higher energy levels, to conduction band. And then those electrons would be available for our circuit. I hope we were able to see, because this is the fundamental concept of band theory: conduction bands, valence bands, and the band gap. Let's stop here. Questions? All right. So let's go to the next part, which is the project. So now when we talk about these bands, there are three types of materials that come out. One are metals, semiconductors, and insulators. When you explain them in terms of the band, for metals, there's no forbidden zone. Either the forbidden zone or band gap is too small, or it doesn't exist at all, which means electrons are readily available for conduction. And as soon as we apply electric field, they are available to fill up new energy states and start moving. Now, when you talk about the diamond structure, all electrons are filled in valence band at 0 degree Kelvin. Conduction band is completely empty, so there's no charge transport because electrons in a valence band are packed on all the sides. They cannot go anywhere. Now, if you were to plot it, we write band gaps like this. We show conduction band lower level, we show valence band upper level, and the middle part is we identify as band gap. Now, this word band gap, you will hear it in many forms. We will call it, we will just write it EG. We will call it band gap. We'll call it band gap energy. We may call it gap energy. So it's a same idea, different names. But just remember, there'll be always G subscript, which will tell us we're talking about band gap, this concept of empty states between two bands of energy, conduction band and valence band. In case of semiconductors, okay, so for metals, they are so close or almost overlapping or overlap that electron doesn't need any energy to jump from. Now, this is another concept. Electron has to get to conduction band before it can travel, because then it has empty sites available to move around. So in an insulator, this band gap is so high that this energy is too high for it to go and jump. So it doesn't go. So in insulator, all electrons keep on filling valence band. They don't go to conduction band, so we don't get any conductivity. In metals, they may be so close or they may be overlapping. So those two bands would be overlapping. Now for semiconductor, their band gap is somewhere in between these two situations. So we say metals so close, either they are overlapping or they are very close to each other. But in case of metals or in case of conductors, in case of conductors, they are so close that they are overlapping or even merging in each other. In case of insulators, they are huge. In case of semiconductors, they're intermediate between metals and semiconductors. So this is then the band gap theory, how we explain the situation into the band gaps and the electrons and how they would behave going up or down. All right.